Good morning, quantum enthusiasts. Today is going to be really great because today we're going to do possibly like the most like coding we're going to do in the whole class. Last time we talked, we were talking about the following subject: how to convert classical code to quantum code that like does the same thing. And the reason we wanted to do this is we want to take advantage of like the coolness of quantum computing, which allows you to not just like plug in, one string of bits into some code, but you can plug in a superposition over many possible input strings into some quantum code, and it will somehow compute all the answers on all the input strings that you in the superposition. So that sounds really awesome, but what it means is we have to figure out how we can sort of do regular old computing, but on qubits, because qubits are the only things that can be in quantum superposition. So last time we mentioned that, like, okay, the most general thing you often want to do is like implement some Boolean function that maps like any possible input n-bit string to like a correct m-bit answer. And f is sort of like the in classical programming like the spec. Like it's like, please make me some computer code in like Python or whatever that implements f. And there's several different ways of doing it potentially. And now we want to think the same thoughts, except implementing f with quantum code. And as we saw last time, we kind of run into a problem because, quantum code in particular has, for example, the property that it's always undoable, which also means that, like, it has the same number of input qubits as output qubits. So, I mean, you can't just do this. Like, in some very lucky cases, like n will equal m, and this will happen to be a reversible transformation, and then you could say, oh, I want quantum code that literally does f on my qubits, and I think you thought about that in your homework. But in general, like, we need to invent like a spec for what it means to compute a quantum or a Boolean function by quantum code, and we talked about several different cases for this last time, and how we'll do it in general and also in specific cases. So I'll eventually remind you of that, but like in this core lecture, we're going to focus a lot of our attention on one special case, which is a very important special case. It's a special case when m equals 1. Okay, so let's remind ourselves about this special case. So the main case we'll focus on today is m equals 1. So it's like a function that just returns one bit, like yes, no, or true or false. It's the kind of function you might name starting with the word is, because you want a yes-no answer. And the most standard way that you should try to implement a Boolean function by quantum code when m equals 1 is by trying to make this instruction. You want to kind of make if f b1, b2 up to bn, then toggle c. Okay, so you want to build a subroutine that effectively operates on n plus 1 qubits, called b1 through bn and c, and has the property that your quantum subroutine like does this. Okay, and the reason we set it up this way is like this is possible, this is eligible to be done, because this instruction, if you will, if you think about it for a moment, is a classical reversible instruction. So in principle, it can be done on a quantum computer, and like, I don't know, this is like a sensible way to talk about doing this. Okay, so I will now tell you, let's say the main claim that we're going to spend some time talking about regarding this main case. So let me write it on the board. And it basically says, if you have classical code implementing f, then you can get like good quantum code also implementing f in this way. So let me write. There is a simple, even, mechanical procedure that transforms. This is kind of about like a compiler, if you will, quantum to classical compiler that transforms efficient, let's say, because many people enjoy this programming language, Python, for example, code for computing f to efficient quantum code doing this. If f of b1 through bn, then toggle c. Okay, so this is, as I said, it's kind of like asserting the existence of like a good compiler that takes as input classical code, such as you might write on Python or Java or C or your favorite programming language, and converts it into quantum code that does this in like a mechanical way. So in a lot of this lecture, I'm going to try to explain to you why this is true. But first, I want to make a few, well, several remarks. So one remark is, in real life, if you will, in these future days when we get quantum computers, you would not actually use this procedure. Well, you wouldn't use the procedure as I'm going to describe it today. Instead, you would handcraft the quantum code. So what do I mean by this? So I'm going to try to convince you today that there is indeed like some procedure that will just mechanically, you put in like your Python or your Java code, and it'll spit out quantum code that basically does the same thing. And I'm going to explain it in a way that like makes it as simple, intuitive, and believable as possible, so that you'll be like, yes, I agree that this is something that can be done. However, I mean, the way we'll actually do it like is not the most like hardcore effective way. And if in real life you were going to like, you're like, oh, I really want to get like, I have a certain f in mind, like the f that, I don't know, checks if a n-bit number is prime, and I really want to get quantum code for this, you probably wouldn't run it through this like mechanical procedure. You'd instead just like directly design it. Nevertheless, I want to spend some time like explaining to you why this is true, and then eventually we'll just like kind of black box this in our mind. I'm doing this just so that we can eventually say like, oh yeah, there's like a simple algorithm for checking if a graph is connected. Therefore, there should be a simple quantum program that's like if B's represent a connected or a B's represent a graph, then if it's connected, then toggle C. So we'll just be automatically like if I can code that normally, then I can code the quantum version as well. Okay. And another remark that I want to make is the following. It's very important, like another important aspect of this claim is these two underlined efficients. Now I could make this more precise by starting to talk about like big O notation and like running time and stuff, but I will not do that in this class. But I do want to say the following, like if you had, imagine you had like a compiler that compiled, I don't know, Python into C, and like it took some Python code that like, on most inputs it ran in like 1 second, and it compiled it into C code that on most inputs ran in like a year. You'd be like, this is very dumb. Like maybe this compiler correctly, like, gave me a correct output, but like I had this nice efficient code, it turned into super non-efficient code. This is just to say like, it's not like that. If your code, Python computes f in a pretty efficient manner, then this quantum code will compute this instruction in a pretty efficient manner using like not too many instructions. So I'll be like a little bit more precise about that later, but I want to emphasize that now. Just because, I mean, you probably know this fact, like for example, this makes a difference. Like actually, for every possible Boolean function, there is some code that computes it, maybe in exponential time. But we don't care about that. Usually we care about computing in like a reasonable amount of time. And this is just to say that like if you know how to compute f in a reasonable amount of time with a classical computer, then you can also compute it in a reasonable number of steps on a quantum computer. Okay. So yeah, now for the next like bunch of time, I'm going to explain why this is true. But are there any questions? Okay. So it goes in a bunch of steps. Like we'll kind of first do like one compilation step, then another, and then we'll finally be done. So let's try to get a good color. Is purple a good color? Let's see. Okay, so step one. When I say Python here, I just mean like any high-level programming language. And in fact, like step one is convert your Python code to Turing machine code. Okay, and how do you do that? Well, this is 251 stuff. This is the Church-Turing thesis, as you hopefully remember from 15251. And if you don't, it basically says like, oh, Turing machine is like an extremely simple programming language. So Python is like a very complicated programming language, or Java is a very complicated programming language. But you know, you saw hopefully in a previous class that you can always convert such code to this very simple programming language called Turing machine, which has the feature that's nice and simple, and it also converts like pretty efficient, you know, code in any language to efficient Turing machine code. So we will not talk any more about this because, you know, this is from like a prerequisite class. And like, actually the first two steps are kind of like all about classical computing. So, you know, this is a course on quantum computing, so we will not dwell too much further on this. So this is some 251 stuff. Okay, so now you have your code that computes f, you know, in like the Turing machine programming language. And step 2, I want to convert it to like another very simple programming language, which I'll call the and or not language. So I want to convert it to and or not code. And what is and or not code? This is like another like programming language that I'm just telling you about for the first time right now. But it looks like this. Here's an example of some code written in the and or not language. You can stare at it while I'm talking. Basically, it's code where like every single line looks like this variable equals either the and, the or the not of some preceding variables. It's a very simple programming language. There's no loops. There's no ifs. There's no indirect memory access. It just looks like this. So why is this possible? That you can convert you know, Turing machine code, which granted is a very simple programming language, Turing machine, if you remember about them, into and or not code? Well, again, this is a topic in classical computing, so I'm not actually going to dwell on it very much. But let me say a few things. First of all, I will have some problems on the homework, the next homework, that's sort of about this, that will like make you even more convinced that this is indeed possible. Second, you also maybe learn about this in 251, depending on how much they talk about the Cook-Levin theorem. Otherwise, you definitely learn about this in 15455, undergrad complexity theory, if you want to take that. But if you don't remember these things, or you don't believe it from the homework, maybe you just believe it from like the general lore of computation, right? Like you probably know from all these videos about like, oh, like build the game of life in Minecraft. Like every computation can be basically broken down into ands and ors and nots, you know? And you take your, you know, complicated code that runs like the game of life or Super Mario, and like you can break it down to like ands, ors, and nots, and then you can make like the pistons that do like ands, ors, and nots or whatever. Okay, so I'm basically not going to talk too much more about these steps. I'm just going to assert that they can be done. Basically, like, by virtue of the fact that, for example, we know there's some simple Python code that can check if a 4-bit string is a palindrome, you know, you should be able to make some and or not code that similarly, like, computes whether or not a string is a palindrome. I think I made this and or not code correctly. I just wrote it off the top of my head. Maybe somebody can check whether this and or code really has the property that the final, you know, output bit value here, C, is indeed 1 if this string is a palindrome and 0 if this is not a palindrome. Okay, I just picked palindrome because it's a very simple kind of function. I should mention also that like people normally don't write and or not code this way or call it and or not code. They usually draw it with these like crazy diagrams that have like bubbles and like lines, and the inputs are on the bottom and the outputs are on the top, and they call it a circuit. But I don't call it a circuit. I just call it and or not code. It just looks like a bunch of lines of code that look like this. Yep. Good, yeah, that's right. Now that you mention it, this should be an and. Okay, maybe I did that intentionally just to check to see if you're, I can always say that, right? Maybe I did that intentionally to check to see if you're paying attention. Yeah, that's true, very good. This person studies and or not code. Okay, one last thing I want to say, and this is really, I mean, we'll see maybe on the homework, or like, you might need to have seen it in previous classes. It's on the subject of this, like, efficiency. And I want to just also tell you that, like, this translation from, like, regular old classical code all the way to and or not code is pretty efficient. And I'll tell you this fact about efficiency, that, like, if your Python, for example, code runs in T steps, I don't know, instructions, time units, then the and or not code that you can produce for it has will have like O of T squared lines. Okay, the notion of like efficiency for and or not code is just like how many lines did you have? This one has like 12 or something. And this is like pretty good. Like if T is like not too much, like 1,000, maybe this is like at most 1,000,000. And in fact, this is like an absolute like worst case upper bound that comes from just like mechanically not even thinking about it and just chugging through these steps in like the most naive possible way. I'll just tell you as like an empirical fact, like if in real life you like handcraft some and or not code to try to do like compute a function f, it's usually has, if your Python code runs in T steps, probably you'll make and or not code that has like order T lines, or maybe T log T lines. So it's usually even more efficient than this. But this is like an absolute worst case like upper bound. And still we don't really mind this. Okay, so basically from now on, I'm just going to like assert this. And what it means is, for this task of like taking classical, let's say Python code for a function f and converting it to quantum code that does this, I'm just going to assume that like you've done these steps and you're starting from this kind of code. And that's a lot better, right? This is a lot closer to like the quantum code that we deal with. Any questions about this? Okay, I guess you're all on board for it. Great. You can imagine like how you might write like and or not code that like computed the sum or the product of two numbers encoded in binary, or checked if a number was prime, or checked if a graph encoded by the b bits was connected. That takes a little thought. But if you don't want to do that thought, you can just rely on the fact that, well, these facts exist that will do it automatically for me.